Hey there, it's Shannon Math Chick Myers, and today we'll be looking at section 7.4, the second part of operational properties. So 7.4 is split up into three subsections, so I'm doing three separate videos for them so it doesn't get too terribly long. Okay, so here we'll be in 7.4.1, we'll be looking at derivatives of a transform. Pretty cool, actually. I liked this section. So here we go. In the next subsections, we'll see how to find the transform of a function, f at t, that is multiplied by a monomial, t to the n, the transform of a special type of integral, and the transform of a periodic function. These last two transforms allow us to solve Volterra integral equations, integral differential, it's a mouthful, huh? Equations, and ordinary differential equations in which the input function is a periodic piecewise defined function. So, starting with derivatives of a function, the Laplace transform of the product of a function, f of t, with t can be found, that just t to the 1, can be found by differentiating the Laplace transform of f at t. If we assume that capital F at s is equal to the Laplace transform of f at t, if we assume that it exists, and that it is possible to interchange, so this is important for the proof, this is not always true, but if it is possible to interchange the order of differentiation and integration, then we have dds of capital F at s, which is our Laplace transform of f at t, and that's going to equal to the derivative with respect to s of the integral from 0 to infinity of e to the negative st times f at t dt, which is the definition, right, for our Laplace transform with the exception of the derivative notation. Now, bringing that derivative inside, we'll get the integral from 0 to infinity of the derivative with respect to s of e to the negative st times f of t dt. And then I'm going to differentiate what's the integrand with respect to s. And so that is going to give us the integral from 0 to infinity of, we'll have a negative t from differentiating the power of the exponential with respect to s times e to the negative st times f at t dt. So this here is all this, and then that's going to end up being negative integral 0 to infinity of e to the negative st, I'll write it like this, times t times f at t dt. Groovy? Now, what does that end up being, of course? That means that the Laplace transform of t times f at t was equal to negative dds of the Laplace transform for f at t, right? The first derivative. Now, if we use this result to find the Laplace transform of t squared times f at t. Sorry if I'm a little slow. I've got COVID, so I'm getting there. All right, so here we go. Let's check it out. We'd have L at t squared times f at t, the Laplace transform, of t squared times f at t is equal to the Laplace transform of t times f at t, which remember we just found that second part. This will be negative d ds of L, the Laplace transform of t times f at t. That's what we just found last time. So let's plug in what we found last time. So negative d ds of negative d ds of the Laplace transform of f at t. Cool so far? So it turns out that we'll get the second derivative with respect to s of the Laplace transform for f at t. So if you continue in this manner, what's going to happen is this. We, of course, want to get this in terms of n. So if capital F at s is equal to the Laplace transform of f at t, then n is equal to 1, 2, 3, ... Then the Laplace transform of t to the n times f at t is equal to negative 1 to the n, so we get the correct sign, because notice they're going to alternate, of the nth derivative with respect to s of the Laplace transform of f at t, which is pretty cool. All right. So now let's look at our first example. We're going to use this theorem to evaluate our Laplace transform that's given. So looking at this guy, we've got t cubed e to the t, right? So this is going to end up being negative 1 cubed, because n is 3, times the third derivative with respect to s of the Laplace transform of f at t, which in this case is e to the t. Cool so far? So we've got that negative 1 cubed is going to have us continue to have a negative, so that'll go along for the ride. And then we're going to need to find the third derivative of this transform with respect to s, which means we have to transform it in terms of s. So this is an e to the positive 1t. So the Laplace transform for that is equal to 1 over s minus 1. And it might be handy to have your in the textbook, or you can search online. There is a table of Laplace transforms. You might want to just print that out and have it handy in case you don't remember them. We use this one a lot, so it's not too hard to remember. So now we got to start to differentiate, right? So this is going to be equal to negative second derivative with respect to s of negative 1 over s minus 1 squared. Using the power rule, the negatives will become positive because there's 2 of them. So differentiating again, we will have negative 2, because that's our power, times or over s minus 1 cubed 6 over s minus 1 to the fourth. Groovy? All right, perfect. Now, let's take a look at the next one. So now we have the Laplace transform of t squared times cosine of 1 times t. So the k in this formula will be 1. So let's check it out. So this will be negative 1 squared, because we're doing second derivative. And then we need to find that Laplace transform. So the Laplace transform is s over s squared plus 1 squared, which is just 1. And then the negative 1 squared will turn positive, and now we need to start differentiating. So we'll do the first derivative. So we'll have the quotient rule, 1 times s times the denominator, which is s squared plus 1, minus the numerator times the derivative of the denominator all over the denominator squared. And then we want to simplify that before we take the next derivative. And so that's going to be s squared minus 2s squared, and then a positive 1. So we'll have 1 minus over s squared plus 1 squared. Cool so far? Now we just need to do another derivative for this guy. So the derivative of that numerator is negative 2s times s squared plus 1, the quantity squared, minus quantity 1 minus s squared times the derivative of the denominator, which will be 2 times quantity s squared plus 1 to the 1, and then times 2s using the chain rule, all over the denominator squared. So we'll have s squared plus 1 squared is to the fourth power. Now let's simplify this a bit. We can take out one factor of s squared plus 1 from each, which will make it a little bit easier to deal with the simplification. So we'll have negative 2s cubed minus 2s, and then minus 1 times 2 times 2s is minus 4s, and then minus negative times a negative s squared times 4s will be plus 4s cubed. And then what else do we have? I think we got everything on that numerator. And that's over s squared plus 1, the quantity cubed. Bringing it on over here, we will get 2s cubed minus 6s over s squared plus 1, the quantity cubed, and then factoring just in case we can divide anything out, which we won't be able to. We'll get 2s times quantity s squared minus 3 over s squared plus 1, the quantity cubed. And we're good to go. Okay, so we're going to use the Laplace transform to solve the given initial value problem. So we have y prime minus y equals t times e to the t times sine of t, which is pretty complicated. We wouldn't want to do an integration by parts on that. And then y at 0 is 0. So using some of our earlier skills, right, we're going to end up, remember that the Laplace transform is a linear operator. So I'll have the Laplace transform of y prime minus the Laplace transform of y is equal to the Laplace transform of t e to the t times sine at t. Cool so far? Okay, so now we're going to go ahead and break this down more. So this is going to give us s times capital Y at s, doing our transform, and then minus y at 0. That's for the very first one. The second one is just going to be capital Y at s. And then over here, what we're going to do here is use part of what we learned from this t operator, and then we're going to use a shift that we learned in 7.3, so a unit shift on the s axis. So here we go. We're going to have, it's the first derivative, so negative 1 to the 1, times the derivative with respect to s of the Laplace transform for e to the t times sine at t. Okay, so now let's work with what we have on both sides of the equation. So we're going to have, if we factor out a y at s to the right side, we'll have s minus 1. And then y at 0 is just 0, I believe. Yep. So this is all equal to negative dds of our Laplace transform of, so now this is e to the 1t times sine at 1t, which we can view as a Laplace transform shifted by a, right, to the right. So here we'll have our capital Y at s is equal to, and I'm just going to keep the s minus 1 as a multiplier until I'm done working with this a bit. So we're going to have negative dds of the Laplace transform of sine at 1t, so our k is 1, but we're going to have s approach s minus 1, and that's because of the 1 in front of the e. Okay? So this means we'll get negative dds. The Laplace transform of sine at kt is k over s squared plus 1 squared, but s is approaching s minus 1, and we still have this other stuff going along for the ride. So then we will have negative dds up. So wherever I see an s, I'm plugging in s minus 1. So we'll get s minus 1, the quantity squared, plus 1. Cool so far? All right. Differentiating, we will have. So this is like the whole denominator raised to the negative 1, right? So we'll end up getting negative 1 times a negative is positive 1 over the whole denominator squared, and then times the derivative of that denominator. So we'll just have 2 times quantity s minus 1 to the 1 times 1. So that, oh good, we've got lots of room. That's going to give us s minus 1 times capital Y at s, which is that Laplace transform. And then we'll have 2 times quantity s minus 1 over s minus 1, the quantity squared, plus 1, all of that is squared. So now is a good time for us to divide both sides by the s minus 1 on the left, right? So dividing by s minus 1, multiplying by 1 over s minus 1, we get to divide out that messy part from that numerator, and we're going to end up with 2 over s minus 1, the quantity squared, plus 1, all of that is squared. Now is when we go and we look at our table of Laplace transforms. We're going to want to use the table. So as you scroll through, you can kind of look at these things. I mean, there's some over here that look a little similar, but we're not quite there yet, because remember, we have a constant. We have a constant 2, which we can get rid of. We can factor that out, or we can keep it. So as we move on, I'm looking here at number 25. Number 25, remember that my k is 1. So I have that 1 cubed, that k cubed. So this is the same as what I have, except mine shifted over 1 to the right. That makes sense? So coming back over here, and sorry, this is equal to y at s. What's going to happen is we're going to apply that linear Laplace transform on capital Y at s. And remember, we have our 2 times our 1 cubed. And so this would be if we look at this as the Laplace transform of 2 times 1 cubed over s minus 1, the quantity squared, plus 1, all squared. And I'll paste that formula here. So looking at that formula, I see my denominator all squared. So I adapt for the change in the formula by having my e to the t, right? So we'll end up with y at t is equal to, and remember, this one is from the e to the a, that's my a, okay? And then this one here is from the k, so this is all from the k. My k in the formula. Okay, and then we'll have e to the 1t because of that shift of 1 to the right from the blue one. And then times sine at kt, so sine at 1t, minus 1t cosine 1t. Those are from the K's. Cool? So, making it pretty, lower y at t is equal to e to the t times quantity sine at t minus t times cosine at t. And this is doing it using tables. And this was from Appendix C in our textbook. Groovy? All right, so that wraps up 7.4.1. I hope you have a wonderful morning, afternoon, or evening whenever you're watching this show. And hey, if you like what I'm doing, hit that subscribe button and like the video. Bye.